Thank you very much, Filippo. It's a pleasure to be here, and I would like to thank also the organizing committee for this kind invitation. So today I'm going to talk about integrity and the shape control of cold spray additively manufactured deposits. This is the outline of my talk. So I would start with a brief introduction about solid-state metal additive manufacturing, what is cold spray deposition, how bonding happens in cold spray, and when does it happen. And then I would move on with introduction to why we are trying to promote cold spray for additive manufacturing and what are the main challenges. Here I have listed a series of main challenges that should be addressed in order to establish cold spray for an additive manufacturing technology. But considering the time, I will be focusing mostly on the two major challenges that we have been working on. If you are interested to know more about the rest of the list, I would be happy to discuss that after the talk, of course. Let's start with a brief introduction to solid-state additive manufacturing. Here in this slide, I'm showing the schematics of the 7 major additive manufacturing techniques that have been established and recognized by ASTM and other international associations. These techniques are well established, commercialized, and are being used in many different, let's say, areas. But as you know, additive manufacturing is expanding rapidly, and every day new technologies are coming along. I've added few newer technologies to this slide that are commercialized still for some niche applications, but not as widespread as the other ones. What is the main difference between, let's say, these new technologies on the right and the ones that are more established and very widely used? Is that if we consider the well-known additive manufacturing techniques to be based on fusion or beam-based, let's say, technologies, means that they are relying on melting of metallic material and rapid solidification in a selective manner, let's say layer by layer, to create a structure. The newer ones that I'm going to talk about, on the other hand, are solid state, so not relying on melting, not relying on thermal energy, but mostly relying on other sources of energy without the risk of, let's say, oxidation and melting of the material. These solid-state additive manufacturing techniques could be categorized to deformation-based one and sintering-based one. So deformation-based means that they are relying on severe plastic deformation to rupture the intrinsic oxide layer around the metallic surface of the feedstock and bond them together. And the sintering-based one are leveraging the atomic diffusion that is induced by reduction of the oxide layer on the surface of the metallic material. So my focus is on the deformation-based technologies, and the first one, that is cold spray. What is cold spray? It's emerging thermal spray technology that is one of the newest within, let's say, this family of spraying techniques. It's relying on acceleration of particles by passing a compressed and preheated gas to a converging diverging nozzle. And as the particles are coming out of the nozzle, if you can run the video, please. As the particles are coming out of the nozzle, they are accelerated to supersonic velocities. They impact the substrate with this high velocity. They undergo severe plastic deformation, and they bond to the substrate. As the new particles are coming along they would bond together and would create a build-up. This is recognized widely as a coating technique. It's being used in many different applications for large, covering, let's say, large areas for corrosion protection or wear protection. I've been working with our team with this, on this topic for many years on coating deposition, assessing the critical condition for deposition of this type of coatings. It's fatigue performance, or the performance of coated samples on the different cyclic loadings, using numerical and experimental studies. But more recently, we have focused on using this technique as an additive manufacturing technology. And that is, let's say, the main topic of my today's talk. But before that, let's know a little bit more about what happens during cold spray and how bonding occurs during cold spray. So once the particles are accelerated to supersonic velocity, they are impacting the substrate because of the severe plastic deformation, adiabatic shear instability, and different types of stability that are happening at the interface, we have the local rupture of the native oxide layer. So the pristine materials are coming into contact, and that's when metallurgical bonding is occurring. Again, because of the severe plastic deformation, we are having some sort of roughening and plastic deformation that is introducing also mechanical interlocking. So a combination of mechanical interlocking and metallurgical bonding are helping, let's say, the bonding and adhesion of the particles in cold spray. But when bonding happens, not always when we are impacting a particle against the surface, we are having the bonding. If we consider specific material, depending on the thermomechanical properties of that material, we always have a range of velocity for those particles that induce bonding. So in this graph, you are seeing the deposition efficiency as a function of particle velocity. And you see that there is a critical velocity that is depending on physical and thermomechanical properties of the material that are ensuring the bonding. So if we are going lower than this velocity, what happens is like what happens during shot pinning. So you are impacting a surface with a shot and it's just rebonding, not necessarily attaching to the surface. If we go higher than this critical velocity, we will have the bonding. And if we go way higher than that, we will have erosion of the substrate. So there is a limited range of velocity that would ensure bonding in cold spray, and that is to be identified for each, let's say, feedstock material and ensured by the process parameters. So as I mentioned, cold spray is very well established for coating, and more recently also for repair, but not for additive manufacturing. Yet it has a lot of potential to be used for additive manufacturing. And why we are promoting that is because there's theoretically no limitation for the thickness of the material that you can deposit by cold spray. There is no limit also for the size of the material that you can deposit, because again, we are not bound to having an environmental chamber because we are not having such high thermal input. So we can increase the size of the deposit as much as our robotic system is letting us. We have very high production rates. I will get back to this in the next slides in comparison with other additive manufacturing techniques. We can get very dense structures with high microstructural homogeneity, high cohesive and adhesive strength. There is no toxic waste to the process. We have compressive residual stresses contrary to the tensile residual stresses that are typical for other additive manufacturing techniques. So it's very helpful also if we think about fatigue performance. Not having the tensile residual stresses is an added value. And of course, because of the low thermal inputs that we have in the process, we can avoid all the, let's say, issues that are associated, as you can see on the right graph, with the beam-based additive manufacturing technique. So we don't have the risk of evaporation, the recrystallization, thermally induced residual stresses, grain growth, and so on. And that is, let's say, an advantage because we can work with materials that are very sensitive to thermal input or to the oxidation. And of course, again, not being bound to the thermal affinity of the material, we can mix materials with different nature, different metallic materials, metals with ceramics. So it gives a lot of flexibility also in terms of gradient structures in the chemical, let's say, composition for multi-material components. And where is cold spray in additive manufacturing space in terms of the manufacturing rate that you can see on the vertical axis? It has much higher manufacturing rate compared to other additive manufacturing techniques that are already established. But again, all these advantages are not, let's say, coming for free, because as you can see, the printing resolution is a big issue. So if we compare the printing resolution of cold spray with other additive manufacturing, it doesn't have such a good resolution for getting very tiny and, let's say, intricate geometries or sharp edges. So there is a long list of, let's say, advantages, but there are still a lot of challenges to be addressed before cold spray is recognized and established as an additive manufacturing technique. So if we want to use cold spray for additive manufacturing rather than coating, that is its, let's say, original area of application, we need to figure out whether it can also be used for a structural application. What is the performance of freestanding cold spray samples under different types of loading. And to study that, we have started a series of experimental campaigns in our lab using the high pressure cold spray system that we have. And here I'm going to show you the results for a nickel alloy Inconel 718. We fabricated dog bone samples with SLM, or laser powder bed fusion. That is a very well-known additive manufacturing technique. And samples with the same geometry also with cold spray. And we compared their performance in order to see where cold spray is standing in terms of structural performance in additive manufacturing area. We did some basic characterization of the microstructure. As you can see, the very anisotropic microstructure of the SLM samples, depending on what cross-section and we have with respect to the building direction. While for cold spray, the microstructure is mainly made by the splats or deformed particles that are packed on top of each other. We have much less anisotropy with respect to the SLM. We performed also a series of post-heat treatment on these samples, starting from specifications for classic materials in aerospace. I'm not going into the detail of the heat treatments, but with the heat treatment, we started, let's say, in the aspirate condition with quiet. You can see the dark areas. These are the pores. By the heat treatment, the porosity was decreased. And here we are having, let's say, in the graph, the quantitative values of porosity. Of course, SLM sample is almost pore-free. These are the SLM samples on the bottom right after different heat treatments. So fully dense, we have higher porosity in cold spray, but still less than 1%. So still totally acceptable in terms of porosity. We performed also X-ray diffraction for residual stress measurements, contrary to very high tensile residual stress values that we have for SLM samples. In cold spray, we have almost 0 or slightly negative residual stresses. And here are the tensile test data on our samples with different heat treatments. In as-sprayed condition, because of the work hardening that we have due to the severe plastic deformation of the samples, we have almost no ductility, as you can see here in this table. But after heat treatment, we have a very clear transition from fully brittle to totally ductile behavior of the samples. We were able to gain 15% ductility. We performed, if we compare with the same, let's say, the same heat treatment on SLM samples, we are in line with the data available in the literature for bulk material. So this is the first indication about the mechanical performance of freestanding samples made of cold spray that after proper heat treatment is similar to what we can obtain with SLM or, let's say, the bulk materials. We performed also actual fatigue tests on these samples. Here you can see the results for stress ratio of 0.1 up to 2 million cycles. The samples, the cold spray samples and SLM samples with the same heat treatment were performing very similar on their also cyclic loading. So this was also the transition, let's say, between the as-sprayed and heat-treated sample, and the ductility that we were observing was also confirmed from the fracture surfaces where the density and the presence of the dimples was much more notable after heat treatment with respect to the originally as-sprayed sample. So the similar performance of laser powder bed fusion and cold spray was very promising here in terms of the potential of cold spray to be used for structural applications. We did a similar study on another material, stainless steel 316L, and here you are seeing the cross-section of the cold sprayed samples in as-sprayed and post-treated condition. Again, the presence of small pores that are decreasing after heat treatment. And in the bottom row, you can see the cross-section in terms of microstructural features and how it evolves as we are applying the heat treatment. So the interface between the particle is where we have, let's say, sometimes limited bonding or the presence of the pores. But with the heat treatment, the atomic diffusion is being promoted, the bonding, metallurgical bonding is increased, and the porosity is decreasing. And here are the results, again, in terms of porosity, the quantified values. Depending on the technique that we are using for measuring the porosity, it's always lower than 1%. And the tensile test data on the top right, you can see the clear variation in terms of totally brittle performance of as a straight sample with the red line. The pointer, unfortunately, is not working always. So I hope you can see the red line that is linear in the graph, and then the very clear transition to the ductile behavior after heat treatment. And in terms of fatigue performance, again, actual fatigue performance 0.1 stress ratio, we got very interesting results. I have compared this with the data available for the same material made of by rolling or forged material or cast or SLM material. Of course, it's not a direct, let's say, numerical comparison, because these treatments, these samples that I could find in the literature are having different post-treatments. But in terms, just to see, let's say, the order of magnitude, it's totally in line with the data that we could find for the same material that are made by other manufacturing techniques, either other additive manufacturing techniques or other standard, let's say, manufacturing techniques. So this was a very interesting sign about the good performance of cold spray samples, freestanding cold spray samples under different types of loading. We studied also the crack propagation behavior in our samples, trying to force the crack to propagate in different directions, either parallel to the build direction or perpendicular to that. Interestingly, we observed an anisotropy in crack propagation depending on the direction that we were forcing the cracks to propagate, and that was due to the packing direction of the splats or the single particles and how they affected the deflection of the cracks. But after annealing, interestingly, the results were very similar to the rolled sheet. So after annealing, we were able to totally eliminate the anisotropy that we had in the as-sprayed sample and get the results very similar to standard manufacturing techniques. With these, let's say, promising results, we started working on cold spray also for composite materials, so combining two different metallic materials, or it's also possible to combine a metallic material and a ceramic material. We did a series of experimental and numerical simulations in order to study how we can control the mechanical performance of these composite material by designing, let's say, the material contribution and the share of each of these phases. Of course, it's not that easy when we are mixing two materials, since the process parameters are unique. The process parameters are mainly the gas pressure and gas temperature, and these are unique parameters. They could be more desirable for adhesion of one of the phase constituents rather than the other. So if we are mixing the particles, let's say the two materials in our feedstock in a 50-50 share, we do not necessarily get the same chemical composition in the deposit, because one of the materials might be more, the parameters might be more favorable for adhesion of one than the other one. So we developed also a predictive model that is a probabilistic-based model in getting input also from experimental data and a series of numerical simulations in order to be able to predict the chemical yield depending on what we have in our feedstock. So if we are starting with a 370% between the two constituent phases, and depending on what materials we have in the feedstock, what would be the final chemical deposition in the deposit. So we have developed this model and we have validated it for a specific case of aluminum and zinc, which is a combination that we have used for having also corrosion protection properties. With cold spray, because of the advantages that it has, it's possible to have different chemical compositions, so have a heterogeneous material in terms of chemical composition, but also it's possible to have heterogeneity in terms of grain size. So this is an example of what we have done in our lab, combining two powders of the same chemical composition, but with totally different grain size, starting from the gas atomized microcrystalline powder and ball milled powder of the same chemical composition, but totally nanocrystallized. And here are the cubes that are taken from the cross section of samples where we mixed these two powders with different volume ratios, 25-75, 50-50, and 75-25 of nano to micro. And here you can see also on the right some of the examples where we didn't pre-mix the powders, but we used two different feeders in order to control also the placement of each of these let's say, powder. So it's possible to get different types of heterogeneity. This is something that is not possible to be done with any other beam-based technologies because of the heat input that we have there. We will totally recrystallize the nanocrystallized phase. So this is a unique possibility to be achieved by cold spray, and we can control the mechanical performance of the deposits by controlling the volume fraction of each phase and also by controlling their arrangement. So till now, I have been bragging about the possibilities that cold spray is bringing into additive manufacturing area, the flexibility that it offers, the structural integrity that is comparable with other additive manufacturing techniques. But there is still a big question to be answered before we can use this as additive manufacturing. And the main issue is the inadequate geometrical control that we have. This is in contrast with the nature of additive manufacturing, because we use additive manufacturing due to flexibility that it offers in terms of geometrical control, right? But cold spray doesn't have that possibility yet. And why this is a big challenge to control deposit shape in cold spray? The main reason is that when we are depositing on a spot or on a, let's say, straight track, the unit shape of the, let's say, this cross section has an irregular, let's say, shape that could be approximated by a Gaussian function. So it's not a very, let's say, regular shape that could be easily superimposed in order to control the shape. As we are increasing the number of the passes on the same track, or we are decreasing the nozzle transfer speed, this Gaussian shape is evolving into a triangular shape. So to make things even more complex, it's becoming even more sharp and changing the form. The cherry on top is that apart from the Gaussian shape, we also have very large spot size. So if you want to compare directed energy deposition, which has a spot size of 2 millimeter, around 2 millimeter, with a much more regular geometry, and here on the right, you see powder bed fusion with much smaller spot size, depending again on the technology, it can range, but it could be in the range of 60 micrometers. So it's much smaller, much more regular shape and predictable shape in compared to the 6 to 10 millimeters spot size and very irregular shape in cold spray. That's why it's so complex to get geometry. Again, this shape is very sensitive to the kinetic parameters of the robot. So if we change the spray angle, if we change the standoff distance, then increase the number of the passes or the feed powder ratio, this shape is continuously evolving and is changing, making it even more difficult to predict the final geometry of the deposit. The common practice right now is that we need to design very complex trajectories with different angles, different standoff distances and speeds in order to control the geometry. And currently, the current application of cold spray for additive manufacturing that is mainly in the aerospace area is relying highly on operator experience, trying to do iterative, let's say, trials to get it right, or relying highly also on post-processing to get the final, let's say, geometry. So this is a big challenge that it has become the bottleneck for cold spray additive manufacturing. What we have done in our group, we have started working on an analytical model that would help us predict the shape based on the physics of the deposition. So considering that we can define the jet particle distribution profile with a Gaussian shape, not always, that's again in parentheses, to make things even more complicated, not always we have a Gaussian shape, but in most cases, let's say the Gaussian form is dominant. So we have defined a function to describe the jet particle distribution profile. We have seen also that deposition efficiency is a function of angle of impact. So another function to consider the effect of angle of impact, and another function, as you can see here, to consider also the effect of the standoff distance. So we have defined a series of partial differential equations based on the physics of the process that are considering, let's say, the effect of deposition efficiency affected by angle of impact and by standoff distance, and also the characteristics of the specific feedstock powder that we are using. And by iteratively solving this partial differential equation, we are able to predict the deposit thickness and how it is evolving as we are changing the parameters. We have applied this analytical model on the elementary unit shape, which is the single track cross section, to see, to validate it for different materials. And here are the results, especially showing how, as we are increasing the number of the passes, the Gaussian shape is evolving to a triangular shape. These are the cross section of the experimentally deposited samples with 10, 14, and 20 number of passes TI64. And here you can see in this graph the comparison of the numerical data, the red lines, and the digitalized images of the cross sections, which are showing very good, let's say, correspondence with the experimental data. Here, in the case of the copper, you can even better see the evolution from the Gaussian shape to the triangular shape as we are increasing the number of passes from 1, 3, 7, 9, 15 to 20 number of passes. So the model is able to capture the effect of the number of passes, is able to capture also the effect of the spray angle. As we are changing the angle of the nozzle with respect to the substrate, the shape of the deposit, its height and its width are changing continuously. So again, here you can see the cross-section of the experimentally deposited sample. And in the middle, you can see the cross-sections that are obtained from the numerical prediction for different angles ranging between 60 to 90 degrees. Also, the 3D prediction of the model is matching very well and is able to capture the effect of the angle of impact. Two other important parameters are the scanning speed, so the transfer speed of the nozzle, and also the spray distance. Here again, you see for TI64, 20 number of passes, changing the scanning speed from 150 millimeters per second to 350 millimeters per second. Again, a very good match between the numerical model and the experimental data, and also for the standoff distance. So the model is able to capture very well the evolution of the shape of single unit shape as a function of different process parameters. As I mentioned, in most cases, we have a Gaussian distribution for the unit, let's say, shape, but that's not always the case. This is an example I'm showing you for aluminum 2024. We have a totally different geometry with much steeper extremities and different inflation points in the cross section. So we validated also the robustness of the model for cases where we don't have, let's say, the typical Gaussian distribution. And also in this case, as I'm showing, for different number of passes and also for different transfer speeds, the model was working quite well. So we went further and we started working on the superposition of the single track. So up till now, we were validating the single track shape as a function of different models. But in order to create a specific geometry, we'll need to superimpose different tracks. So here, trying to get a more vertical wall, we superimposed a 90 degrees track with 260 degrees on the sides. And again, the quality of the prediction is good. So the error is not propagating as we are increasing the number of the passes. And also we validated the model for cases where we don't have a planar substrate. So this would be a more complex shape where we are having also a curved substrate, and that is affecting the dynamics of the deposition during cold spray. So the model is working very well for all the cases that we have developed till now, but we are still predicting spot geometry. So moving from spot to spot prediction to a automatized tool pass planning, that is the case for other additive manufacturing, there's still a long way for that. For other additive manufacturing techniques, there are already commercialized software that you give them the CAD file, they will give you the slicing, let's say, or they directly comment to the robot, and everything is already automatized. But in the case of cold spray, we are way behind that. So we are trying to develop the model, the analytical model that have been defined for towards, let's say, tool pass planning. The problem is that it has a very high computational cost. So it takes us a lot of time because it's in an iterative solver to solve all the partial differential equation system. And as we are increasing the number of the passes, as we are increasing the size of the component to be created, it takes much longer time to define the pass. And it's also very sensitive to the mesh size and the time steps, so the quality and the accuracy of the results would be reduced if you are going to upscale, let's say, the geometry. A good alternative would be to use deep learning approaches because they are much more flexible and much more efficient in terms of time and speed to predict, to do, let's say, this type of calculation. The downside is that they would need a very large size data set in order to have a good fidelity in terms of geometrical accuracy. So to address this, what we have come up with is to use our analytical model, so leverage the robustness of the physical model that we have developed in the past and generate a set of data to be fed to a neural network algorithm in order to predict the shape and enhance, let's say, the computational efficiency of the whole process. So we set a set of input data that are the main major, let's say, important parameters that are affecting the shape: number of passes, horizontal coordinate, transfer speed, spray angle, and standoff distance. And we use our model to generate the data set to be fed into neural network algorithms to predict the 2D and 3D shape of the deposit. Here is, let's say, the variable process parameters that we selected for full factorial DOE, a total of 2,400 calculations made by the analytical model. And we also, on top of that, we added a series of optimization functions to make sure that we are improving the geometrical accuracy of the deposit, including the fact that we would like to have to design, let's say, the hatching distance in a way to reduce the surface waviness of the deposit. Since this is a continuous process and we cannot stop the deposition during the process, if we have a very complex shape, the scanning strategy would become very important to minimize the oversprays or the waste of the material. So again, designing the scanning strategy and minimizing the deceleration and acceleration of the robot that would affect the quality of the shape of the deposit is again another function that we considered. And also, if we have geometries with notch or any geometrical discontinuity, it's also important to make sure that we are correctly following any variation in the cross section. So we consider also an adaptive slicing function in order to adapt the thickness of the layers as it is following different, let's say, geometrical curves. I'm showing you a demonstrator for application of this hybrid, let's say, approach. The demonstrator has concavities in order to validate the robustness of the scanning strategy designer. And it also has a variable cross-section to validate the effect of the slicing, the adaptive slicing approach. It's not really fair to do a direct comparison between the analytical model and the deep learning approach because they have different concepts. They are written in different languages. One is Python, the other one is MATLAB. The concept is different, but I'm just comparing the duration of the analysis just to give you an idea about how more efficient is the second approach with the first one. So our analytical model takes 2 hours and 16 minutes in order to predict the shape of this demonstrator, while the hybrid DNN-based model takes just 32 seconds. So it's a very good, let's say, it gives an idea about how more efficient could be this hybrid approach in order to enhance the efficiency, the computational efficiency of shape prediction for cold spray, and it would help, let's say, boosting the application of cold spray in that area. To conclude my talk, I'm just giving you one slide where we are trying to develop and use this code, not just for additive manufacturing, but also for local repair and for welding. So we are adapting this code also for cases where we have small cavities that could be local or true cavities, or even for different geometries of welding, where we can use the advantages of cold spray for eliminating any heat-affected zone to do repair or to do welding. So that's also very important to predict the shape, to minimize the overspray, minimize the waste of the material and the post-processing machining in these cases. These are, again, examples of how we plan the scanning strategy to fill specific geometries of defects. And with that, I would like to summarize my talk. In the first part, I'll show that cold spray, freestanding cold spray deposits have a very high potential for structural applications, as their static and fatigue performance can be comparable to other additive manufacturing techniques or to standard, let's say, bulk materials. And by pairing also analytical methods with deep learning algorithms, we can obtain control on the shape of cold spray, boosting, let's say, its way towards additive manufacturing, not just for additive manufacturing, but also for repair and also welding. And the next steps for us are to combine these two stages of prediction of the mechanical performance and prediction of the shape together, so that we can provide a platform that can give an idea about the shape and the mechanical performance of the cold spray deposits for additive manufacturing at the same time. I would like to thank and acknowledge, of course, the contribution of my colleagues and my team who have contributed to all the results that I was presenting today. I would encourage you to check our website if you are interested to know more about cold spray and its application. And with that, I would like to thank you all, and I would be very happy to answer any questions.